Section 12 of The Outline of Science, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Michelle. The Outline of Science by J. Arthur Thomson. Chapter 21. The Romance of Chemistry. Part 1. When we first visit a great museum, we are impressed by the multitude of different kinds of things. These thousands of startlingly different species of animals, each itself and no other, these hundreds of different kinds of wood, shelf after shelf of minerals, and Aladdin's cave of precious stones, besides all manner of things artificially made, such as alloys and fabrics, drugs and preserved foods. Some of the objects we see may fade into one another, but what almost embarrasses us is the number of things that are quite distinctive. We get the same impression of diversity when we take a walk in the country, or when we see a dredge or a trawl brought up on deck, shuffling the chemical cards. Now, a kindly curator in the museum might take us to the bird cases, for instance, and show that, after all, the diversity was in great part due to different shufflings of a not very large pack of cards. There are thousands of tunes, but there are not many notes. He might take us to the case of minerals, where by ourselves we got the impression of overwhelming and baffling variety, and show us that a comparatively small number of really different things may be shuffled into a multitude of diversities. A small cast of players may form a great variety of different tableaux. There might be in the museum a case showing a sheet of parchment paper, a slab cut out of a tree, a wooden pot full of glue, a cork for the same, a piece of India rubber for erasures, a celluloid beaker full of water, a lead pencil, a vulcanite holder, a pad of blotting paper, a lump of sugar, a little starch, and 100 other things, as different could be, including even a diamond. And yet the label of the case might correctly state that all this variety included only 3 elements: carbon, hydrogen, and oxygen. Perhaps this is one of the big revelations of chemistry for ordinary people, that in spite of the immense variety of things in the world, there is only a relatively small number of things that are really different, namely, the 80 or so chemical elements. We do not know how many words there are in the English language, but there are only about 26 generally recognized letters. It is the same in chemistry: many different hands, but not such a large number of cards. Furthermore, just as there are some letters like Q and Z which are not in very frequent use, in the same way it must be noted that many of the 80 or so chemical elements are rare, and do not occur in more than a small percentage of the specimens in the museum. Many of the rare earths, though very important for man's purposes, do not play a large part either in the architecture or in the bustle of the world. They lurk quietly in remote corners. Take tantalum, for instance. It has been calculated that there are, on a very moderate estimate, 250,000 of very different kinds of things in this world of ours. But scientific chemistry has shown that this multitude is due to varied groupings of about 80 really different kinds of stuff, namely, the chemical elements. It is not easy to put the case rightly, for each fresh pattern may be something very definitely new and individual, just as a painter makes many pictures of the same few colors. Everyone knows the variety of patterns that result when the pieces of colored glass in a kaleidoscope are shaken into new combinations, but this is a static diversity. It suggests, however, what may result from the shuffling of a few elements, especially when some of these are what is sometimes called attractive. In general terms, the conclusion to which common experience and exact science lead us is this: that given a small number of sociable elements, there may be many a ménage. From a few elements, even from fewer than we can count on the fingers of our 2 hands, there may be a new world. And the view is widely held among chemists that there has arisen from one elemental stuff the whole array of known elements. Section 1. In a previous chapter, The Foundations of the Universe, the problems which the physicist and the chemist of to day are so eagerly investigating were fully discussed. We saw there how it has come about that all the observed phenomena of chemistry and physics are regarded as indications of the fundamental unity of matter. All matter, in short, is supposed to be, in its final analysis, essentially the same in constitution. The atoms of all matter consist of particles of positive and negative electricity. The simplest atom, that of hydrogen, is a unit of negative electricity, called an electron, revolving around a nucleus of positive electricity called a proton. Electrons obtained from different atoms are found to be the same. In an atom of hydrogen there is one electron, in an atom of helium two, in an atom of lithium three. The addition of further electrons to the system gives rise to the atoms of all other elements. All matter is thus supposed to be electrical in its nature. The atom, since its disintegration is seen to take place, is no longer the atom indivisible or incapable of being broken up into something simpler. It is not now believed that each of the 80 or so elements known to us has its own kind of atom, each stamped with its own properties. The properties and qualities of the different elements, it is believed, depend on the number and arrangement of the particles of negative electricity (electrons) and of positive particles (protons) contained in the atoms of the various elements. The view is that all the elements, though they have different chemical qualities, are built up out of the same material. Thus our ideas regarding the constitution of matter and the framework of the universe have been completely changed. The superlatively grand question is, what is the inner mechanism of the atom? It is the business of the chemist to attempt to fathom the mysteries of the properties of the various chemical elements, to evolve order and system out of them. It is to the chemist that we owe our knowledge that the atoms of different substances can be arranged in a definite order, and also that they show an increasing complexity of structure. Heavier atoms appear to behave as though they were evolved from the lighter. Forms of matter. It is well known that under suitable conditions the same type of matter can exist in three distinct forms: solid, liquid, and gas. In passing from one state to another, it is a matter of common knowledge that there are remarkable changes in appearance and physical qualities of an element. These changes are believed to be connected with the average distance which separates one atom or molecule from the other, and in the rapidity of motion. In the gas or vapour form, the molecules are on an average so far apart that their mutual attractions are relatively unimportant. The lowering of the temperature, the distance and rapidity of motion of the molecules diminish until, under certain conditions, the attraction of the molecules for one another predominates, resulting in a much closer packing in the appearance of the liquid form. The molecules, however, still retain a certain freedom of motion, but this is diminished with the lowering of the temperature, until at a certain stage the molecules form a tighter grouping, corresponding to the solid state, where the freedom of motion of the individual molecules is much restricted. In order to account for the resistance of solids to compression or extension, it has been supposed that the force between molecules is attractive at large distances, but repulsive at small distances. While we are able to offer a general explanation of the passage of an element from one state to another, a complete explanation of such phenomena will only be possible when we know the detailed structure of the atoms and the nature and magnitude of the forces between them. It is well known to everybody that the atom of one chemical element may combine with one or more atoms of another element. When the chemist speaks of the valency of an element, he means the number of other atoms with which one atom of this element can directly combine. For example, one atom of hydrogen combines with one atom of chlorine, and the result is hydrochloric acid; or one atom of oxygen will combine with two atoms of hydrogen, and the result is water. One atom of nitrogen combines with three of hydrogen, and we get ammonia. Each of these combinations represents a chemical process, that is to say, a chemical change which produces a substance which is totally distinct, not a substance which merely partakes of the characters of the two component elements. Thus are the various substances built up. The elements are mostly found in mutual combinations, and the combinations are sometimes of course very complex. While a particle or molecule of water consists of two atoms of hydrogen and one of oxygen, The molecule of the proteid, called albumin, is built up by 72 atoms of carbon, 112 atoms of hydrogen, 18 atoms of nitrogen, all brought into association with one atom of sulphur. In all protoplasm of living matter there is a mixture of proteins, carbohydrates, and fats, with intricate chemical and physical interrelations. It is highly improbable that there is any one substance which deserves to be called the living matter or protoplasm. What we actually know is a complex and heterogeneous system in which various chemical reactions take place simultaneously. There is always involved, as life goes on, a breaking down and a building up of proteins. But the riddle is still unread. Some biologists hold the view that there is an ultimate molecule of life hidden in the protoplasm, which holds the secret of the endless building up and breaking down. Sir Ray Lankester gives this supreme life stuff the name plastogen, and he says in regard to its workings that whilst they can be grouped with the chemical and physical qualities of other bodies, they so far transcend them in complexity and in immensity of result, the whole creation of plant and animal life, that their appearance constitutes in effect a new departure, a sudden and to us unaccountable acquirement. But then we must remember that it is also an unaccountable thing to us that water suddenly becomes ice at a low temperature and suddenly becomes vapour at a high temperature, even if we are able to imagine the mechanism which necessitates these changes. We cannot explain the nature of things, even though we can classify them and arrange them in order, and more or less satisfactorily guess what their inner mechanism is. We cannot, in our present state of knowledge, trace them in detail to a first beginning. Section 2. Some of the elements in their natural conditions are gaseous, like oxygen, hydrogen, nitrogen, chlorine, etc. Mercury and bromine are liquids, while a great number, chiefly metals, are solids, like gold, iron, zinc, etc. Professor Meldola says with respect to the distribution of the elements: "It is of interest to note that more than three-fourths of the accessible crust of this globe upon which we live is made up of two non-metals, oxygen and silicon, about one half being oxygen. Nothing affords more striking evidence of the marvel of chemical change than the contemplation of this geochemical fact, that the superficial solidity of the earth is due to the predominance of those mineral constituents into the composition of which gaseous oxygen and the non-metal silicon enter to a preponderating extent. The whole crust of the earth with which geology deals is composed to the extent of more than 99% of only about 20 out of 82 elements." This will give an idea of the rarity of some of the materials which the chemist has had to deal with. Mixtures and compounds. There is an obvious but important difference between a mixture, like sand plus sugar, like iron dust plus chalk, and a compound, like sugar or like chalk. A mixture is never homogeneous. It can be divided into different ingredients. A compound is always homogeneous. Its particles, however fine, are all the same until we begin to break up the compound into its components. With water we can dissolve away the sugar from the sand. With a magnet we can pick away the iron particles from the chalk. But it is usually necessary to take more thorough-going measures to split up a compound. It must not be supposed, however, that the distinction between a mixture and a compound is always easy. Air looks very homogeneous, but it is a mixture of a great crowd of oxygen particles, a still greater crowd of nitrogen particles, and small crowds of carbon dioxide and water vapour particles. Nothing seems more homogeneous than water, but pure water is never found in nature. There are always impurities in it, and one needs only to bring a glass of cold water into a warmish room to see how multitudinous bubbles of gas form on the inner walls of the vessel. These suggest, at any rate, that there is a good deal of gas mixed up with water. If this were not the case, no animals could breathe under water, for while water is a compound H2O of hydrogen and oxygen, it is not possible for animals to separate the two components the way plants are able to do with the carbon dioxide CO2 mixed in the air or the water. Perfectly pure substances, though often advertised, are very difficult to obtain. They are indeed almost ideal, which led a great investigator to say that Chemistry is the science of substances which do not exist. Traces of impurity in a substance are often of great practical importance. They sometimes influence the properties of the substance in a remarkable way. We quote a sentence from Dr. Mellor's admirable text book, Modern Inorganic Chemistry (1920). H. Vivian says that 1,000th part of antimony will convert the best selected copper into the worst conceivable. Lord Kelvin says that the presence of 1,000th part of bismuth in copper would reduce its electrical conductivity so as to be fatal to the success of the submarine cable. And W. R. Roberts Austin says that 1/500th part of bismuth in gold would render gold useless from the point of view of coinage, because the metal would crumble under the pressure in the die. Molecules and atoms. A mixture can usually be separated into its ingredients by more or less simple mechanical means. A compound cannot be broken up into its components without going beyond simple mechanical methods. We break a piece of salt into finer and finer powder, but each particle of salt dust remains salt. If we could get hold of a particle which would cease to be salt when we broke it in pieces, that particle would be a molecule of salt, and we should have divided it into groups of constituent atoms, sodium atoms and chlorine atoms. A lump of salt is built up of a prodigious number of molecules of salt, and each molecule is a little building of which the atoms are the bricks. To return to the elements. An element has been defined as a substance whose molecule contains only one kind of atom. But this definition must be modified in relation to the fact that the elements uranium and thorium give rise, as we shall see, to other elements different from themselves. Nevertheless, the general idea remains that an element is a unique and homogeneous kind of matter. When an electric current is passed through water, H2O, it decomposes it into hydrogen and oxygen. Bubbles of oxygen may be collected at one pole and bubbles of hydrogen at the other pole. This is a fact. There is a theory, perhaps more than a theory, that free atoms of oxygen travel in one direction and free atoms of hydrogen in the opposite direction through the water. Ion, the Greek word for a traveller, is the term applied to these particles which travel to the two electrodes during electrolysis. Ions are travelling atoms or groups of atoms which are started on their journey by the dissociation of the electrolyte, say water, and they are believed to carry opposite charges of electricity. Each molecule that is split up gives rise to two kinds of ions: anions going to the anode pole, and cations going to the cathode pole. And these two kinds of ions are furnished with equal and opposite charges. The ion with a positive charge of electricity is attracted to the cathode, or negatively charged electrode, and the ion with the negative charge is attracted to the anode, or positively charged electrode. And each ion will then be relieved of its charge and become an ordinary atom again. The speeds of the migrating ions have been measured, and it seems that the heaviest ions, for example, with the greatest atomic weights, move fastest. It has been supposed that this is due to the more slow-going ions dragging along with them a number of molecules of the solvent. This is very theoretical, but everyone knows the practical application in silver plating and the like. A brass spoon, let us say, is immersed by a wire in a solution of silver salt, say a solution of silver cyanide in potassium cyanide, and the spoon is the one pole, the cathode. A sheet of silver is the other pole, the anode. A weak electric current is passed through the fluid, and cations of silver are then deposited on the brass spoon, which becomes a silver plated spoon. Mr. C. T. Kingset, in his Popular Chemical Dictionary, says of chemical changes: "All articles of food and clothing, the materials of which our houses and buildings are constructed, and which are needed for their decoration or repair, every art and every industry, all depend essentially for their production or activity upon chemical changes, as realized in nature or made by man to serve human purposes. The same is true of the production and decay of animal and vegetable matters, as also the process by which they are broken up and the resulting products made available in their turn as food for new life. These chemical changes constitute a sort of adaptation of matter to environment, and in essence are acts of creation, as every such change produces products which, although related, are quite distinct in character and in properties from the original substances which give rise to them when subjected to the required influences. Thus, in a very literal sense, all matter, which, as will be seen in other places, appears to be essentially one in nature, is actuated by a spirit of life, being susceptible to change when the environment is appropriate. Chemical change. Chemistry is concerned with the different kinds of matter in the world and with the changes which they produce by interaction. If a bar of iron is heated it becomes longer, but it returns to its original length when cooled. We call this a physical change, for the iron remained iron from first to last. But when a piece of iron left out of doors begins to rust, we call this a chemical change, for the iron becomes something different, namely, iron oxide, with quite different properties. This iron rust is not transmuted iron, but iron in combination with oxygen, and that is a very different thing. Chemical changes always imply a shuffling of the cards, a new arrangement of partners. Pie man plus pie, as the American expositor puts it, on the one side, boy plus penny on the other side. A change occurs, and the situation is pie man plus penny, and boy plus pie. This sort of thing is going on ceaselessly all the world over. It is necessary to say, however, that the boundary line between chemistry and physics has become very indefinite, especially in light of the fact that the qualitatively chemical differences between uranium and radium, or thorium and radium, seem to depend on quantitatively physical differences in the corpuscles of electricity. Demonstrating the invisible. Many of the materials with which the chemist deals are invisible, and so is the air we breathe, as long as it is dry and clean. In ordinary circumstances none of us ever sees oxygen, hydrogen, nitrogen, or carbon dioxide, and yet all of these are as real as iron and lead, sulphur and diamonds. As Professor James C. Phillips says, "A gas may be without smell or taste, it may be as intangible as a spirit, and as for seeing it, why, it may be off and away while the observer still thinks he is looking at it." Now, it is worth while pausing to ask how the chemist is so sure about what he cannot see, why he must reject the proverb, "Seeing is believing." Invisible materials betray themselves by what they do. The oxygen rusts the iron. The carbon dioxide which we breathe out into a beaker of lime water makes the water cloudy. A mouse lowered into a shaft containing the deadly carbon monoxide gas is killed. The danger of this poisonous gas escaping from a leaking or badly burning stove is well known. White mice used to be carried by submarines in order to detect the dangerous CO gas. But there are finer methods now in use. When a tumbler is inverted into a basin of water we cannot press it quite down, and we know that the rise of the water is being resisted by the invisible air in the tumbler. Sometimes we can ourselves almost lean up against the rapidly moving invisible air. Still more convincing is the test by which Lavoisier founded modern chemistry, the test of the balance. For every invisible material has its weight, even the hydrogen, which is 14½ times lighter than air, and therefore lifts the balloon so easily. We do not need to go any further in indicating how chemistry demonstrates the invisible, but it would be dull indeed not to refer to the modern demonstration of invisible gases by turning them into liquids or solids. Section 3. Liquification of gases. Modern science has given us a vivid picture of that condition of matter which we call gaseous. Professor Clerk Maxwell compared the molecules in calm air to a swarm of bees, when every individual bee is flying furiously, first in one direction and then in another, while the swarm as a whole either remains at rest or sails slowly through the air. But we have to add to the picture the collision of one bee with another bee, for a molecule can travel only a short distance, its mean path, without striking another. Indeed, as Clerk Maxwell calculated, the number of collisions which a molecule must undergo in a second must be reckoned by thousands of millions. In his famous discourse on molecules he spoke of the time it took for the smell of an opened bottle of ammonia to pervade the room. The molecules of the ammonia have a velocity of 600 meters per second, but they are not able to spread at that rate through the room. They strike against the molecules of air and are delayed. Each molecule of ammonia is so jostled about by the molecules of air that it is sometimes going one way and sometimes another, and like a hare which is always doubling, though it goes at a great pace, it makes very little progress. Gradually, however, the ammonia gas does spread through the air of the room. In a liquid, as contrasted with a gas, the molecule has hardly any free path, but is always in a state of close encounter with the other molecules. In a solid, the molecules have almost lost their opportunities for moving about. Now everyone knows that water vapour may condense into flowing water, and that this may freeze into solid ice, which may melt again and steal off as a mist. Saturated steam above 720.6 degrees centigrade is a gas. Thus water occurs in four states. The passage from phase to phase is familiar, but in the liquification of gases it became dramatic. About the beginning of the 19th century, Northmore and others liquefied sulphurous acid gas by pressure, but progressive research on the liquefaction of gases began with the work of Faraday and Sir Humphry Davy in 1823, when chlorine, carbonic acid, ammonia, and other gases were liquefied by great pressure. Later on, Thélaurier showed how the evaporation of a jet of liquid carbonic acid produces cold so great that the rest of the jet is frozen into fine snow. There is a temperature above which no amount of pressure will produce liquefaction, and it was not until devices for securing very low temperatures were discovered, and this was a great achievement in modern science, that it became possible to liquefy oxygen, nitrogen, and the like. But with the invention of methods of obtaining very low temperature, which brings the molecules close together, just as heat drives them apart, oxygen and nitrogen were conquered, and in 1898 Professor (now Sir James) Dewar produced liquid hydrogen. As Professor Tilden remarks, "It was both interesting and gratifying that the final victory, which crowned the long series of successful attacks upon the apparently impregnable position of the permanent gases, should have been recorded in the laboratory of the Royal Institution, where the first successes in this field were won by Faraday." Section 13 of The Outline of Science, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Michelle. The Outline of Science, Volume 3, by J. Arthur Thomson. Chapter 21. The Romance of Chemistry, Part 2. Transmutation of Elements. The chemists or alchemists of the Middle Ages sought after the philosopher's stone, which would transmute base metal such as lead into gold. Some even believed that their quest was successful, for the science of chemistry was not far enough advanced to dispel their illusions. If a knife blade be placed in a solution of blue vitriol or sulphate of copper, it comes out like copper, and, as Professor James C. Phillip points out, to the alchemist the result admitted of no other explanation than that the iron had been converted into copper. We know now that no such change takes place. Some copper comes out of the solution and is deposited on the surface of the iron, while by way of holding the balance even, an equivalent amount of the iron passes into solution. The transmutation of one element into another was discredited when the science of chemistry began to get on its feet, and just as naturalists believed in the fixity of species, so chemists believed in the immutability of the elements. Each element is itself and no other, but everyone knows the change of view that the discoveries of the 20th century have brought. It is now established that the element uranium may in part change into radium and some other elements. A spontaneous change occurs, associated with the partial disintegration of the uranium atom, which leads to the formation of minute quantities of radium, apparently with ionium as an intervening link. From another changeful radio element, namely thorium, there may also be derived at a very low rate minute quantities of radium. It appears that the uranium and thorium give off particles of helium, an element first detected in the sun and restricted, as far as the earth is concerned, to minerals containing the two radio elements just mentioned. The final product of the metamorphosis appears to be lead, and in this way a radioactive mineral may be utilized as a geological clock. Professor Soddy explains this. In a uranium mineral, each 1% of lead in terms of the quantity of uranium signifies a lapse of a period of 80 million years. Errors, of course, are possible,
If lead should have been an original constituent of the mineral, but these are minimized by taking a large number of different minerals. On the other hand, every cubic centimeter by volume of helium per gram of uranium in a uranium mineral signifies 9,000,000 years, and as here helium, being a gas that forms no compounds, cannot have been initially present, and as moreover some will have escaped, the age of the mineral by this method is a minimum, whereas the age by the lead content may be too high. The carboniferous rocks tested by this new method appear to have an age of some 350,000,000, and the oldest Archean rocks of over 1,500,000,000 years. The difficult subject of radioactivity has been referred to in other chapters, but it cannot be more than touched on in a work of this scope. Enough has been said, however, to show that the doctrine of the unchangeableness of the chemical elements requires revision. We have already quoted from Professor Soddy, well known as one of the brilliant pioneers of the study of radioactivity, and we select a summing up sentence. The radio elements are in course of spontaneous mutation into other elements, and the process proceeds through a long succession of more or less unstable intermediate elements until the final stable is reached. In the domain of things this is the nearest analogue to evolution in the realm of organisms. Section 4. Chemistry of the living creature. Of the 80 and more elements, no fewer than 29 are known to occur in living creatures, but 12 of these are rare. Those that are always present are hydrogen, carbon, oxygen, nitrogen, phosphorus, sulfur, potassium, magnesium, calcium, and iron, and to these there should probably be added sodium, chlorine, and silicon. Not uncommon are iodine, for example, in brown seaweeds and the thyroid gland; manganese, a trace in most animals and in some plants; bromine, in brown seaweeds, a trace in some animals; and fluorine, in bones in a few plants. The first big fact is that the elements invariably present in organisms are common in the inorganic world. The second big fact is that the essential and most important elements in living creatures are hydrogen, carbon, oxygen, and nitrogen. In most animal and plant proteins, sulfur is also present in addition to the big four. In nucleoproteins, like the chromatin of the nuclei of all cells, there is likewise phosphorus. As far as the constituent elements go, there is nothing peculiar in living matter. On or near the surface of the cooling earth there would be a natural abundance, the chemists tell us, of water and CO2, and in this triumvirate there is a unique ensemble of fitness for forming the stones and mortar of the house of life, unique, for instance, in the synthetic possibilities of carbon, in the solvent power of water, in the stimulating power of oxygen set free by the dislocation of CO2, and in the attractive capacity of all three, drawing in other elements, such as magnesium and iron, to serve fresh purposes. It may be of interest to notice individually some of the common elements that occur in living creatures. Hydrogen ions are very important in respiration and gastric digestion. Oxygen is a releaser of energy in vital combustion and an attractive agent bringing in other useful elements. Water, H2O, is a chief constituent, over 70%, of living matter. Nitrogen combines with carbon, hydrogen, oxygen, and a little sulfur to form proteins, and all living implies the building up and breaking down of proteins. It gives living matter its restless explosiveness, because it is loath to combine with and easy to dissociate from most other elements. Carbon is unique in its capacity for forming compounds, of which more than 100,000 are known, and its combination with oxygen, CO2, affords the source from which most of the free oxygen of the air is derived. The remarkable power of carbon. The chemistry of carbon is of a peculiarly interesting nature. Because of its remarkable power of uniting with itself as well as with other elements, it is enabled to build up single molecules containing very large numbers of atoms, and such molecules form the basis for framing the structure of living organisms. Without these two properties of the carbon atom, life, at least as is known upon the earth, would be impossible. It is this element, in combination with a few other elements, for instance, hydrogen, oxygen, and nitrogen, which gives rise to a multitude of compounds of every degree of complexity, and out of which many substances are produced which are essential in building up the bodies of animals and plants. As we have seen, living products are chiefly based on four elements: carbon, nitrogen, oxygen, hydrogen. From these four elements, with admixtures, most substances of the living world are made up. It is a curious fact that all life on the earth should depend on two single factors: one, the presence of a mere trace lying at the level of only between 3 and 4 parts per 10,000 of this gas, carbon dioxide, in the air; and two, the natural power of the carbon atom contained in the carbon dioxide of entering into energy relationships with fellow carbon atoms. Given these conditions, a suitable form of energy and a suitable transformer for that energy, capable of turning it into chemical energy of carbon compounds, and it follows that all the complex constituents which form the basis of life not only can but must arise. As we have seen in a previous chapter, the energy transformer is the green plant cell aided by the green coloring matter called chlorophyll which it contains. It is interesting to note that carbon exists on Earth in different forms. There are 3 modifications of it to be found, all very different in outward appearance, and it may be added of different values in human estimation. We have carbon in the black and opaque form of charcoal, and as graphite or common blacklead, and in the transparent crystalline form of a brilliant diamond. All of these are merely different forms of the same stuff. And yet, although successful efforts have been made to manufacture artificial diamonds, it has not been found possible to do so on a commercial basis. That is to say, it is still cheaper to procure them by expensive means from the natural resources than to manufacture them in the laboratory.
The regulation of vital phenomena. Sulfur in small quantity is an essential part of the CHONS compounds called proteins. Phosphorus is necessary for the formation of chromatin, which is so important as a vehicle of hereditary characters. It is essential in the formation of tissues so different as bone and brain. Potassium is the most active of metals biologically considered, and its salts play an important part in the regulation of vital phenomena. Magnesium is an essential constituent of chlorophyll, in the making of which iron is also necessary though not included in its composition. Iron also occurs in the red pigment of the blood which captures oxygen from the outer world. Calcium compounds play an important part in stimulating or slowing vital processes. So we might continue, but we have said enough to suggest the manifold ways in which the various qualities of elements are utilized in the service of life. Section 5. Circulation of matter. One of the epoch-making ideas in science is that of the circulation of matter, a corollary of the idea of conservation. It is an old idea, for one of the Greek philosophers, Heraclitus, is responsible for the epigram, "All things flow," but its demonstration belongs to the 19th century. Just as we associate the name of William Harvey with the circulation of the blood, so we should link the name of Justus Liebig (1803 1873) with vivifying the fact of the circulation of matter. Many people know the name of this great chemist in connection with beef tea, but he has greater claims for commemoration. Everyone knows how the clouds condense on the cold rocks of the mountains, how the drops of water flow together into runlets, how they fill up the bog moss sponges and overflow into streamlets, how these make rivers which join the sea, how the sun-drawn mist rises from the ocean and forms the clouds which break on the mountainside. So the world goes round. But this is far too simple a case, for we have been dealing with water from beginning to end. Let us take a better case. Circulation of nitrogen. All living matter includes the nitrogenous carbon compounds called proteins, such as white of egg and the gluten of bread. In other words, all living creatures require nitrogenous supplies. Animals obtain these by eating other animals, or by eating plants, so we may leave them for the moment out of account as far as the problem of nitrogen supply is concerned. The question is where plants obtain nitrogen, and the generally valid answer is that the roots absorb nitrates and the like from the soil.
There is abundance of nitrogen in the air; indeed, 4/5 of the atmosphere is nitrogen. But this treasure house is closed to plants, except in the case of sundry types which, with the help of partner bacteria (see Sir Ray Lancaster's article Bacteria), are able to capture the nitrogen in the air which the rain brings down into the soil within reach of the rootlets (see the article on Botany). Leaving the exceptional cases aside, we see that plants depend on nitrogen compounds in the soil. Where do these come from? Electrical discharges in the atmosphere lead to the formation of nitric acid and nitrite of ammonia, which the rain brings into the soil. Various soil bacteria help to change nitrites into the more useful nitrates, on which the plants largely depend. But it must be admitted that other soil bacteria, which cannot be credited with philanthropy, work in the opposite direction. But when we pass from the extrinsic supplies of available nitrogen, such as thunderstorms and leguminous plants may afford, we face the fact that one cosmic generation lives on the graveyards of its predecessors. The bread we enjoy is a rehabilitation of the guano deposited by the birds of ancient sea cliffs. What we have just begun to do in illustrating the circulation of matter may be readily elaborated, and the idea may be extended to other elements. It should be kept in mind, however, that only a few elements share in the main circulation, for only about a dozen are always represented in living creatures, and a not much larger number makes up 99% of the earth's crust. But in an outline like this, the important thing is to make clear some of the germinal ideas of the science. And this is one, that many of the elements of the chemical world often change their partners in their unending dance. Catalysts. When we turn from a chemical treatise of a generation ago to one of to day, the whole atmosphere seems to be different, and one of the changes is suggested by the word catalysis, still unfamiliar to many. What does it mean? There exist certain substances, says Professor R. K. Duncan, which may lie in a vessel seemingly inert, and yet by their mere presence may dictate what action shall or shall not take place. A thing which has this commanding power is a catalyst, and the process is catalysis. The peculiar feature is that the substance which exerts a catalytic influence is not affected by what it does. It can be used over and over again. The presence of a very small quantity of platinum causes the combination of large quantities of oxygen and hydrogen, but it is not exhausted in the process. Professor Duncan gives a good example. Chromium chloride is a curious substance that exists in two forms, soluble and insoluble. The insoluble violet crystals may be left under water for days unaffected, but drop into the test tube a trace of chrominous chloride, even 25/1,000,000th of a gram, and the violet crystals hasten to bury themselves in the water. The temperature rises, and an indigo blue liquid results. The mere presence of a trace of the catalyst has suddenly let loose the powerful affinities lying latent in the violet crystals, and the substance is dissolved. It is almost as curious as though a pound of salt thrown off the battery should dissolve Manhattan Island. This is an example of what is called physical catalysis. For the chemical properties of the chromic chloride are the same after as before it is simply passed into solution. Ferments. To be included among catalytic substances, yet conveniently separated, are the ferments or enzymes produced by living creatures, for example, yeast plant and bacteria, or by living cells like those of the digestive glands. The fact that the yeast cell, the diameter of which is only 1/3000th part of an inch, is capable of so many chemical changes is one of the unexplained wonders of the world. As in the case of inorganic catalysts, so with these organic ferments, minute quantities can bring about chemical transformations of great magnitude, and at a very rapid rate. The number of ferments is legion, and they work like magic. Quickly and quietly they bring about changes which in the laboratory would require powerful reagents and high temperature. They are not living, but they are essential to life. They are always in a colloidal state, and they effect many different kinds of change, though each usually does only one thing.
They help in building up and in breaking down. The changes they bring about take place most rapidly at a certain optimum temperature, and the ferments are susceptible to the influence of other substances, such as salts. Some always work in couples. As examples of organic ferments we may mention the ptyalin of the saliva, that changes starch to sugar; the pepsin of the stomach, that changes protein to peptone; the trypsin of the pancreas; and the diastase of the green leaf, that alters the solid starch into fluid transportable sugar. We know what these organic ferments are able to do, but we do not know what they are. Indeed, there are so many unsolved problems before the investigator of ferments, that the darkness seems almost greater than the light. Facts are rapidly increasing, but a rationale of the facts eludes us. 6. Crystals. We have spoken of crystals. Little is known of the determining cause of the formation of crystals, and the subject is too complicated a one to be dealt with in this work. The science of crystals is concerned with the study of the definite geometrical forms assumed by elements and compounds under certain conditions. The structure of a crystal consists of a small group of atoms which assume a regular arrangement in a fixed pattern. For instance, in a crystal of rock salt, which is built up of sodium and chlorine atoms, each sodium atom has 6 chlorine neighbours, and each chlorine atom 6 sodium neighbours, arranged in a manner typical of rock salt crystals. The atomic distance of these is about 100,000,000th part of an inch. Many chemical bodies assume the crystalline state when they change from liquid or gaseous condition into the solid form. They may be produced, for instance, by the evaporation of saturated solutions. It has been stated as a statistical truth that everything strives towards symmetry in so far as the environment will allow. Diamonds. A large number of definite chemical bodies are found in nature in crystalline conditions, such as the diamond. The diamond is the purest form of crystallised carbon. In the diamond every carbon atom is symmetrically surrounded by 4 other carbon atoms, arranged at the corners of a tetrahedron in such manner that the whole crystal is one continuous molecule, thus explaining, as it is thought, its great density and hardness. A crystal arouses our interest by reason of the regularity of its form, the perfection of its surfaces and angles, its transparency and brilliancy. A perfect crystal, like a diamond, is quite transparent and colourless, although it possesses that marvellous "fire" which we see oscillating with every movement. But most precious stones are tinged with grey, yellow, or brown. It is due to the high qualities of refraction and dispersion of light that diamonds give off the beautiful flashes of blue, gold, and red fire. Other colours, such as ruby red and emerald green, are more rare. The colour of many precious stones is really produced by minute proportions of impurity. The continued study of the formation of crystals, it is thought, may throw further light upon electrons and their connection with the structure of the atom. Colloids. Another set of facts of first rate importance relates to what is called the colloidal state of matter. In 1861 the Scottish chemist Thomas Graham noticed that some substances pass readily through a parchment paper, while others diffuse very slowly through. He called the latter colloids, from the Greek kolla, glue, and the former crystalloids. Weidewagen and gum may illustrate colloids, sugar and salts crystalloids. But as many substances can exist as both, it is better to speak of the colloidal and the crystalloid conditions of matter. Moreover, the colloidal condition may be fluid, and then it is called a sol; or it may be gelatinous, even solid, and then it is called a gel. In any case, matter in the colloidal state is in the form of ultra microscopic particles of solid, or droplets of fluid, in suspension or in other manner of dispersion in another solid, liquid, or gas. The study of the properties of the colloidal state has proved of great importance in chemistry, and it is of fundamental interest to the physiologist, for living matter is in a colloidal state. Professor Bayliss writes: "Protoplasm in the living state has the properties of a liquid system, containing, however, particles of solids and droplets of immiscible liquids in a freely movable state. Many vital phenomena are bound up with the colloidal properties of the physical basis of life." We have said that many rare elements, though very important to us, lurk quietly in remote corners. Rare earths and their uses. Iron is common, but gold is comparatively rare. To get 2 ounces of the metal gallium, a great chemist has to work over nearly 600 pounds of crude material. But aluminum is easily procured. Why are half of the known elements so rare that few people know their names? As Professor R. K. Duncan writes: "Who, for example, has ever heard of, much less worked with, lanthanum, europium, erbium, neodymium, gadolinium, thulium, praseodymium, terbium, ytterbium, samarium, holmium, tantalum? Yet these forbidding names represent certain elements of matter, just as do others, such as sulphur, phosphorus, or lead, elements, too, unique in their properties and filled with all kinds of potential usefulness to man. We cannot answer this plain question, why are so many of the elements so rare? It may be that they are so rare because they are always changing into something else, or it may be that they are being made from other elements which are also rare. A significant fact is that the dozen rare elements mentioned above are found associated together as if they formed a family party. Let us pass to something easier, man's use of some of the rarities. Towards the end of the 19th century, Carl von Welsbach hit upon the brilliant idea of increasing the incandescence of a gas flame by making it heat up a cotton mantle impregnated with a rare element, such as lanthanum. Various improvements followed, but the principle remains the same to day. The cotton mantle was replaced by a fabric made of China grass, and the lanthanum was replaced by 99% thoria and 1% certuria, two rare earths which work into one another's hands in some rather mysterious way. The theory is obscure, the practical result is brilliant light. In 1897 Professor Nernst of Göttingen showed that a filament made of rare earths (thoria or zirconia) was at ordinary temperatures a non conductor of electricity, but a very good one when heated, even when lighted by a match. So we got the Nernst electric lamp, which gives a far finer light than the ordinary carbon filament electric lamp, but has the disadvantage of various complications and delicacies. Other rare elements have been tried, each with its own virtues. Thus there is a lamp with a filament of the very rare osmium, probably the most refractory and unalterable solid known to science, and therefore furnishing a filament with a very long life. There is another with a filament of the unrustable, steel hard element called tantalum, which occurs in South Dakota and in Australia as part of the mineral called columbite. Still more recent, and also very efficient, is the lamp with filaments of the rare metal tungsten. It must be noted that there are many effective lamps, such as the carbon lamp, which do not use rare earths, but it is of interest to realize that some of the rarities among the elements are common in the lamps of our houses and streets, and that academic curiosities have become of everyday practical utility. But man has not been able to devise a light as economical as that of the firefly. And yet we cannot pass from this subject without some appreciation of the progress that man has made in the art of producing light. It is a sort of index of his ascent. This was well expressed, for the time, by Sir William Crookes' preface to the first edition of Faraday's Chemical History of a Candle. From the primitive pine torch to the paraffin candle, how wide an interval! Between them how vast a contrast! The means adopted by man to illuminate his home at night stamps at once his position in the scale of civilization. The fluid bitumen of the Far East blazing in rude vessels of baked earth; the Etruscan lamp, exquisite in form, yet ill adapted to its office; the whale, seal, or bear fat filling the hut of the Eskimo or Lapp with odour rather than light; the huge wax candle on the glittering altar; the range of gas lamps in our streets, all have their stories to tell. All, if they could speak, and after their own manner they can, might warm our hearts in telling how they have ministered to man's comfort, love of home, toil, and devotion. This was well said, but we have had a glimpse of what might be added thereto, of incandescent mantles made of rare elements gathered, often laboriously, from the far corners of the earth; of delicate metal filaments whose toughness is such that the resistance they offer to the passage of electricity produces a most excellent brilliance; and of subtleties on the inventor's horizon which promise still more perfect light. A story about helium. The element helium was first detected in the sun by means of the spectroscope. It was 25 years later before it was recognised upon earth. How important and unlooked for results may follow from scientific investigations and discoveries is illustrated in this case, as in many others. Helium is chemically inert. Like argon, it unites with no other chemical element. It is wholly indifferent to them all. This means that helium cannot be burned. In this connection a curious story is told. It is the next lightest gas to hydrogen, and unlike hydrogen it is non inflammable. In the late war the belligerents anxiously searched for a gas to fill airships which would be light and non inflammable. The great drawback to the German Zeppelins was that they were filled with a highly inflammable hydrogen. The Allies made a discovery, thanks to a wide awake enthusiast who suggested helium. But helium was enormously expensive to produce. However, there are in Texas certain gas wells which yield helium. Large plants were constructed with haste to recover helium from the natural gas by means of liquification, with successful results. Mr. C. G. Abbott tells the sequel. The matter was, however, kept a well guarded secret. Even the name was hidden. Photographs of the plant taken were labelled "Argon Manufactories." The idea was spread that the purpose of the experiments was to produce a new variety of poisonous gas for warfare, or perhaps a special variety of gasoline for use in aeroplanes. All sorts of camouflage were adopted to prevent the enemy from learning the true purpose of the experiments. So far had the work progressed that at the time the armistice was signed a consignment of 150,000 cubic feet of helium was on dock at New York, waiting to be sent to France to be used by the Allies for their balloons. Plans were on foot for increasing the output of helium enormously, so that it was probable that had the war lasted until the summer of 1919, the Allies could have employed helium gas for observation balloons and for Zeppelins with entire immunity from all possibility that they could be shot down with incendiary bullets. This may serve as a final diagrammatic instance of the endless ways, ever increasing in subtlety, in which the chemical world intersects with that of human life, both in its heights and in its depths. CHAPTER 22